Welcome to this video on Introduction to Machine Translation. So machine translation is basically converting an input sequence into a desired output sequence, and it's usually used or referred in context of translating one language to another language. So for example, let's say we have to translate English into Hindi, and we have this sentence, how are you doing? And we have to translate this into Hindi, which translation to Hindi is आप कैसे हैं. So in this case we have an input sequence of five words, let's say x1 to x5, where we are assuming that the question mark is a word in itself, and the task is to produce the output sequence of words which translates this sentence into Hindi, and the number of words in the output might or might not be equal to the number of words in the input. For example, in this case the output sequence has just the 4 words, and input sequence has 5 words. So the most popular model to do this translation is encoder decoder model or attention model. These are known as sequence to sequence models, and these are RNN recurrent neural network based models. So, and we have two types of these models, either encoder decoder based models or attention based models. I would say that this is a generalized case of encoder decoder models, and encoder decoder can be considered as a special case of attention based models. So let's look into the architecture details of encoder decoder and attention based models for machine translation. Let's look at the sequence to sequence neural networks. So in these networks we are given an input sequence x1 to xn. Let's say these are the words of the input language, words in the input sentence, and we have to generate an output sequence where y1 to yn dash, where n may or may not be equals to n dash. So any of these cases might hold, and yi are the words in the output language or the output sequence. So this task is now the machine translation, and so we will discuss two models for this, encoder decoder model and attention model. So the limitations of encoder decoder model is that it works poorly on long sentences, and we'll see soon why this is cases. And the limitations for attention model is it's comparatively more costly in terms of computations. So first let's see at the encoder decoder architecture. So this is a diagram for encoder decoder architecture. In encoder decoder architecture we have a input recurrent neural network. So all the words in the input sequence x1 to xn pass through a recurrent neural network. And if you are unfamiliar with what a recurrent neural network is, please feel free to Google, or I'll post another video about that. So this assumes that you are familiar with basic recurrent neural networks. So the input sequence is passed through the recurrent neural network, and finally we obtain a compressed representation of the input sequence. Compressed representation of input sequence, and then we pass this representation to another neural network. So this is our second recurrent neural network. We pass this to the decoder neural network. So this is known as encoding part, when we create this encoding, and then we decode this encoding to generate our output sequence y1 to yn dash. So we pass this encoding as an input to this, as an initial input to this neural network, and then basically we also pass the outputs from the previous inputs, and at each time step we obtain these YIs. So now to obtain these YIs, we have basically two strategies. One is greedy search. So basically what greedy search simply does is that, let's say we have to first find y1. So for all the vocabulary words, let's say we have V words in the vocabulary, capital V words in the vocabulary, it calculates the probability of each word given. So probability of each word wi in vocabulary given the input context x. So where x is basically all these input words, x is basically x1 to xn. So let's denote x1 to xn by capital X. So it calculates the probability of each word given x, and let these probabilities are denoted by p1 to pv, p capital V, and then it picks the word with maximum probability. Let's say that word is wk. So the output y1 becomes wk, the word with the maximum probability at this step, and this output is fed as an input to the next step along with our previous recurrent neural network state. And again, for all the words, we try to again predict that probability for all the words in vocabulary given that x and y1. So given x and y1, we again try to calculate probability for each and every word, and we find the word, we pick the word with the maximum probability, let's say wk plus 1 as might not be the next word in the vocabulary, so wj, some arbitrary index j, as our next prediction, and this continues. So given the previous outputs, all the previous outputs, and given the input vectors x, input words x, we each time predict the probability of the next. For all the words in the vocabulary, we predict that the probability of having this word as the next word, and we just simply predict that word to be the next word. So in practice this approach works, but this does not always produce the best solutions, doesn't always produce the concise, neat and clean translations from one language to other. So another strategy is known as beam search. So the beam search works in the following way. Let's say you have again V words in the vocabulary. So what beam search does is that it at each stage it considers k possibilities, where k is known as beam width. So what I mean by this is that, let's say it calculates the probability of first word. So these are the probabilities of probability wi belonging to v given initial context. So let's say we are generating y1. So for that we calculate these probabilities, and then we pick k words. Instead of one word, we pick k most likely first words. So we pick k most likely first words and let those words are w1 to wk, and 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 for all these keywords we can further consider that what would be the second word given the first word. So basically, given w1, we will find what would be the probability of wi belongs to v given x and w1. And let's say these probabilities are denoted by p1 to pv here. Similarly, for w2, it will again calculate the probability of all the words. So in total, we will calculate the joint probability of the first and the second word, and we will have kv such probabilities, kv such possibilities. For each k, we consider v possibilities for the next word. And among these kv possibilities, we again choose k out of these possibilities. So at each step, we just maintain k out of these possibilities. And so now we'll again, let's say these w1 are those k possibilities. So these w1s are not single words anymore. These w1s are the k topmost possibilities out of these kv possibilities. So this might be I am, this might be you are. So these are like, these w1 to wk would be then duplets. And now for the third word, we will again consider the joint probability of, let's say first two words are there, what is the probability of the third word. And so this expression here would change into that what is the probability of word wi given x, I and m. So given these words were obtained previously, what is the probability of the wi? And again, since we maintain k options at every stage, and we for every k options we look at all the v words, we attach each stage we again have kv possibilities, and we keep on choosing k out of these possibilities and keep on doing it again till we obtain our final answer. So basically we can say that grid search is a particular case of binary search when k is equals to 1. So at each step we just pick the best word and we go along with that. So this is how the encoder decoder model functions. So the basic limitation of encoder decoder function is that only the output to the last neural layer in the encoding sequence is passed to the decoding sequence. Only the output from only an is passed to decoding sequence. So if the length of input sequence is very large, then an might not contain sufficient information about a1, a2, the words that appeared initially, that is x1, x2. An might lose some information about these words, and hence for longer sentences the encoder decoder architecture tends to perform poorly when the length of the sentences increase. And to tackle that, we have another architecture known as attention model, and let's see into the details of attention model now. So let's see into the details of attention model. So let's say we have to produce the output sequence as y1 to yn and dash, and we are given input sequence as x1, x2, xn. So here we are using a bidirectional neural network, bidirectional RNN as our encoder. So this model is similar to our encoder decoder model, except that instead of just passing the information from AN to our decoder model, to our decoder RNN, we pass information from all the words. That is, we pass information of A1, A2, AN in a weighted sense. So it will become clear soon. So first let's look at this architecture. So we have a forward unit here, let's say F1. It feeds into F2, it feeds into F some arbitrary R, where R is greater than 1 and less than n, and it goes on and ultimately feeds into an Fn. So this is basically forward recurrent neural network. Similarly, we have B1 backward network, Bn minus R, Bn minus 1, Bn. And we concatenate the forward and backward representations, hidden representations, to obtain A1 to AN. So these are the hidden representations from encoder. And so now earlier what we were doing is that we were passing only AN as the input. So this C1 was basically earlier equals to AN, and it's no longer equals to AN now. So we were just passing this Cn to be equals to AN in our decoder sequence, and we were not passing all of these A1 to AN into our decoder sequence. But now what we want to do is, like, we want to pass all of this. So idea behind that is this, and I'm just marking that will also pass the previous input basically. So the idea of passing all the words in A1 to AN is because Y1 is most likely dependent on A1, because let's say in our example, how are you doing, and आप कैसे हैं. So how is dependent on कैसे? So it's like that. It's like y1 is dependent on, is more likely to dependent on few initial words, let's say x1 to xm. So y1 is more likely to dependent on the initial words rather than the later words. And so why don't we pass all the hidden representations A1 to A capital N in a weighted manner, where weights are given by alpha 1, alpha 2 to alpha n. So basically here C1 is basically summation of alpha I AI. So we pass these hidden representation in a weighted sense, where I is from 1 to n, and this C1 is now used as an input to the decoder to calculate output y1. Similarly, for C2 we will again find the separate weights. Let's say beta 1, beta 2, and let's say beta capital N. For C2 we'll again find separate weights, and will pass the weighted sum. C2 will be basically sigma of beta I ai, I is equal to 1 to n, and we pass this context along with the output y2 y1, sorry, the previous output y1 to generate y2, and this continues on till we generate the full sequence. So this is the basic idea behind the attention mechanism. Now the question remains is how to calculate these weights alpha is or beta is. So one of the properties of alpha is that we calculate these weights such that the sum of these weights is 1 and all of these weights are positive or 0. So to calculate alpha I, first we need to calculate something which we called as EI, which is kind of like to see that how much this weight should be. So clearly this weight should depend on A1, right? Alpha 1 should clearly depend on A1. Similarly, alpha 2 should clearly depend on A2 because it's a weight on A2. Alpha 2 is simply a weight on A2. But all these alphas should also depend on B0. B0 is like what is the previous information of decoder? What is the information of decoder till now? Which are the words which we have seen earlier? And depending on the words which we have seen earlier, these weights would be decided. So basically, in principle, to decide alpha I, we need to see what is AI. That is, to decide alpha I, we need to see what is AI, a relationship between these, and we also need to see that what is the encoding, what is the hidden representation so far, bi minus 1, and we can pass ai and bi minus 1 through some neural network to calculate EIs, where I is from 1 to n, and then we can use a softmax over these EIs to calculate alpha s, so that the sum of alpha is to be 1. To make the sum of alpha is to be 1, we can use the softmax approach. So in this example, to calculate alpha i's, we will pass like to calculate alpha 1, we will pass A1 and B0 through some neural network to calculate alpha 1. Similarly, we will pass A2 and B0 to calculate alpha 2. Now to calculate beta 1, we will pass A1, since beta 1 is dependent on A1, and we'll also pass B1 to the neural network, because whatever the representation we have obtained so far, plus for which we have to generate our weight, that is A1. So and we'll learn these weights as and along the back propagation, which we will do for the entire network. So so one more example. So here beta 2 will depend on a neural network which takes input as A2 and B1, right? So B1 and A2. Similarly, beta n will depend on AN and B1, where beta is the weight for the second output. So I hope now it is clear to you how attention model works. It's slightly confusing, but once you look into it carefully, it becomes quite trivial and intuitive. And I might be creating another video to implement a machine translation or sequence to sequence model. I hope you like this video. Please feel free to share and subscribe. Stay tuned, as more and more good content is coming soon. Thank you.